Assalamu alaikum. Today we are going to discuss observability. This is a concept similar to the controllability. In case of the controller design, we have to have the ability to control all the state variables, which was a requirement for the design of the controller. So state variable feedback gains cannot be designed if any state variable is uncontrollable. So uncontrollability can be viewed, as we have seen, that in a diagonal system based on the matrix B, we can see if any one of the row was becoming 0, then you can say that that particular corresponding to that particular location, that state is uncontrollable, and then your system you cannot design for controller. Okay, so for that particular similar concept that we already have in case of our ability to create a design for the observer. So the thing is that the output of the system using the output of the system, we have to deduce the state. So based on the output, whether we can calculate or estimate the state variable or not. This is a requirement in case of observer design. So if any state variable has no effect upon the output, then we cannot estimate that state variable by observing the output. So the ability to observe a state variable from the output is based, we can also see it from the diagonalized system. So the similar diagram that we have done previously, we can use the similar idea, but previously we have seen whether they're connected to the input side or not, all the states. This time we are going to see whether all of them are connected to the output side or not. So if all of them are connected to the output side, then we can actually predict the states based on our output and the input. So this is what we are trying to look in using the similar kind of figure. So previously we have noted whether these lines are available intact or not. This time what you have to check is that whether we have the other lines that is going to the output, whether they're available or not. In this particular example, these are all 1 by S, 1 by S, 1 by S. So whatever the gain, basically they're connected to input. So from this side, you can say, I estimate whether the system is controllable or not controllable or not. And from the other side, we are going to investigate whether the system is observable or not. So if somehow one of them are missing, like say this is the scenario. Okay, so then this X1 have no effect on the output. So by observing the output Y, we cannot estimate what will be the value of X1. So the system cannot be observable. So the definition, according to the definition, if the initial state X, if initial state X T0 can be found from UT, which is input, and YT, which is output, and which are measured over a finite interval of time. From T0. So from T0 to some interval of time, say T, we have measured the input and the output, and based on that, if we can estimate what will be the value of XT, then the system is called observable. And if it is not, or if it is not, then you call that system is unobservable. So for unobservable, if you want to go for a pole placement technique for observer design, in that case, this will be the criteria that you are looking for. So observability is the ability to deduce the state variables from a knowledge of the input, which is UT, and the output YT. So pole placement for an observer is a viable design technique only for systems that are observable. So from the figure that we have seen that in the first case, which was with the blue one, we have seen that y equal to cx, and we have seen that 1, 1, 1, all of them was linked with the state. So now output is linked with all the states. So your system is observable. Okay, so observable. And if y equal to the next one, the red one that we have seen is 0, 1, 1. So x1 state is not observable. So we can say that the system is unobservable. Okay, so this is observability by inspection. So first method, similar to the controllability, is by inspection. But the difficulty again is the same difficulty that you have seen, is the system has to be diagonalized. System has to be diagonalized. Okay, so but there is it is not reliable as before, as we have seen in the controllability, because of the multiple poles. It may happen that by observation it seems not observable, by inspection it seems not observable, but it in real life it can be. So that is why we have something similar to the controllability matrix, which is known as observability matrix. So observability matrix. And the definition is something like this. If an nth order system or plant with the characteristic with the equation represented by x dot equal to ax plus bu, y equal to cx, this is the scenario, then the system is completely observable, is completely observable if the matrix OM, observability matrix, equal to C, CA, C square A goes up to C A, CA square and up to C AN minus 1 is of rank, is of rank N. Okay. So only then, so similar criteria, different metrics, and if this is giving a rank of N, then your system is completely observable. So quickly, let's see one example. Example 12.6. So x dot equal to ax plus bu equal to 0, 1, 0 represented in the phase variable form. -4, -3, -2, x plus 0, 0, 1 always, and your output y equal to cx equal to 0, 5, 1 x. So if you want, you can draw the you can go for drawing the signal flow graph, and if you draw it, what you're going to see is that your output 1, then 1 by S, 3 consecutive, this is a third order system, so the 3 consecutive integrator is there. If it's variable form, so the feedbacks from the X3 is basically -2, -2, -3, and -4. -4. So this is definitely your X1, X2, X3. Now look at the output. Output Y is not related to the X1. So rather it is 5X2 and X3. So 5X2 and X3. So 5 and 1. So as you can see, X1 is not related to Y. So the idea that we get it from here by inspection is that the state X1 is not observable. So, but as I said, that the best result by inspection is always observed or obtained in case of a system represented in diagonalized or parallel form, and the system was also not having multiple poles. So this result cannot be true. So let us try to check whether by inspection that we are saying that state X1 is not observable, whether that is true or not. So our observability matrix OM is CA square goes up to CA to the power n minus 1. So in our case, n is 3. So CA square will be our observability matrix. So the value of the C is the first row that we have, 0, 5, 1. Then A matrix will be multiplied with this one. So first of all, this column will be multiplied with that one. Then it will be set in the first location. So basically, it will be 0, 0, -4. So -4 will be sitting here. Then the second column will be multiplied with that one. So it will be again 0, 0, -3, which will be your next column value. And the third one will be, you're getting is 0, 5, -2. So 5 minus 2 is 3. Okay, so once you have this value now, so you're supposed to have CA squared. So you already have CA, then you have A. So basically the new value that you have, -4, -3, and 3, that will be multiplied with your A matrix, that is 0, 1, 0, 0, 0, 1, -4, -3, -2. So it will give you 0, 0, and 3 minus 3 is minus 3 into minus, so -3 into -4 is -12. And then you have next one is -4, then -3 into 3 is 9, so -13. Finally, third one will be 0, -3, and -6, so basically -9. Now this is your observability matrix. Now next thing that you have to do is you have to find out the determinant or the magnitude of your observability matrix. And that if you just do calculate the value, you're going to see that the value is -344. So since the determinant is not singular, basically system not 0, So in the rank of the observability matrix is basically 3, which is same as the order of the system. Order of the system. So we can conclude that the system, or even though by inspection the X1 was not observable, but in reality the system is completely observable. So you can go for the pole placement technique for this one. So in another example, if you want to check with the other one whether it system is observable or not, 12.7. So if signal flow graph is given in this time, and 1 by S, then 1 by S, and then you have again 5 goes to output. So this is minus 21 by 4, and this is minus 5. And the output y is 5x1 and 4x2. So let us first of all find out what is the system, represented system, the x dot equal to. So as you can see, the system is a second order system because we have two integral, that is 2 1 by s. So ax plus bu. And now we can see that our x dot, which is this one, is our x dot equal to what we have is x dot equal to x2. So basically phase variable form, so 0 1. And what about x2 dot, x1 dot? Previously it was x1 dot. Now x2 dot equal to what do you have? Input you have, then you have minus 21 by 4 x2, as well as we have a feedback from x1 with minus 5. So minus 5 minus 21 by 4 x plus input is going to the second one, so u. And what about C matrix? Y equal to output y equal to cx. That is, C is basically 5 4. It goes with x. Now, by inspection, this all the states, a state variable seems to be observable because output is linked with both of them by observation. But let's check with the observability matrix because the system is not diagonalized. So OM is this time C and CA. So C is 5 4, and then 5 4 will be multiplied with that one. So basically 0 and 5 minus 20, and then it will be 5 divided by 5 minus 21. So basically minus 16. So now this is the observability matrix. Now, if you find out the determinant of the observability matrix, what you're going to see is that it will be minus 80 plus 80. So 0 or singular. So the rank of this one is not 2, rather 1. So rank of OM is not 2, which was the order of the system. So as you can see, our system is not completely observable. So we cannot apply the pole placement technique for this one. So next, inshallah, we'll be discussing alternative approaches to observer design. Similar thing we already have seen for the controller design. Okay, see you in the next class, inshallah.